Okay, so very good morning to you. Today we are meeting because we are in the first part of our two-day workshop on advanced data analysis. We'll be using of SPSS, and basically when I say data analysis, I would specifically refer to the econometrics techniques that we use about the inferential statistics. In other words, our center of gravity would be throughout these 2 days would be the regression, but not just simple regression, but we will go different aspects of regression. But before I go first, I hope you can share you can see the screen. I can show you the variable view here. You can see that the data which I have taken in the absolute numbers, for example, total revenue is a absolute number. It doesn't go very well. Either you must have a ratio. For example, you need to find some relative measure. For example, total revenue divided by total assets or something, or you can find the logarithmic values. And as you can see that this name look very strange, but if you start looking at one by one each letter, it looks like natural log of total revenue. The idea behind not taking the absolute values is that the size effect can come into the picture. So the companies which are bigger sized, despite they're not so efficient, despite all the limitations they have, they can take undue advantage of being big sized organizations. So that's why to neutralize this impact, discount this size effect, we either take the ratio, we divide there is a numerator and a denominator. As I said, in this example, it could easily be total revenue divided by total assets or something like that here. But I have taken log values because that log value also make the data non-linear. If the data is linear, like with the absolute number, then the danger is that the predictability or the randomness of the data is lost, and which is not a very good thing to have. The second variable which we have is the operating profits return. Of course, it's a ratio, and it's not an absolute variable, it's a relative variable. And the return on capital employed is also calculated by dividing something with something. The annualized firm stock returns, we all know we all have studied finance, the first lesson and course, and we have seen that these are the relative measures. So technically, all the variables, and here I made different forms of stock return. Sometimes I call the squared values because sometimes it doesn't work with so sometimes your y variable, even the x variable, the dependent variables and the independent variables, if you take them only in the linear form, it doesn't work sometimes. And just because a certain form of the variable doesn't show the significant results, it doesn't mean that the phenomenon doesn't exist. It may mean that our existing model in the existing form of the variable is not enough to detect the cause and effect relationship. So this is why I have the firm stock returns, but I also squared them. I even found the logarithmic of this natural log of squared value. And at some stage, I also took the cube values, so to make it even more nonlinear. And at some stage, I took the exponential annualized stock returns. I didn't come across any problem in this case, but the message I'm trying to say to you is that if you look at the row 4, 5, 6, 7, 8, you can explain, you can describe, or you can, transform the variable into various forms. There's no guarantee always that if you have in the linear form, the variable, it would work. The linear form means, for example, look at this price to earning ratio. It's a linear form. There's nothing squared, nothing cubed. Debt to equity ratio is as it is. As we see in the theory, we just calculate based on that. So these are the linear formed variables, but sometimes when the relationship is not promising and we have some heartbreak, then we must consider that is it the problem with the way the data is explained, the way we have calculated the variable? Is it the problem that the phenomenon is there, but we don't have enough tools and transformations of the variables to spotlight that phenomenon? Okay, so therefore, be prepared that you might have to sometime change the appearance, the looks of the variable, which in technical jargon we call transformation of the variable. All right, and one more thing I did was that, even though I'm just repeating that the decimal point, sometimes your variable is very small, so you need to make sure that you have enough decimal places. I think SPSS by default gives you 2 decimal places. If the numbers are big, then you can even do with 0 decimal. But I have seen in my data that there are many, many, many small values. So I took up to 4 decimal places, okay? And I don't think you need to make any change here. And then we go to, wait a sec. So the market record. So in this case, as you can see the list of variables, I think that we choose debt to equity ratio as a dependent variable. We also call it explained variable or predicted variables. And then we can consider all other variables as independent variables, explanatory variables, or predicting variables. So this way we can carry on our discussion. But just make sure that before you start analyzing, just see that this looks quite neat and clean, which it looks to be. And then we have our data view. And the last variable is D2E, and which I'm planning to use as the dependent variable, okay? So I hope you all know that our starting point is analyze. We go to regression, we go to linear regression, and then we have this dugout. In the dugout or in the activity area, we first pick up our dependent variable. And then I'm not considering too many variables. That's not a bad idea because it's the first iteration. So I can take all other as. And then slowly, as the discussion will build up, we can delete some of the variables. But let's have the first encounter. Nothing to be changed here. Enter is fine, even though sometimes people can use stepwise. Stepwise means that you can have various models which SPSS fixes based on rigor, but I think enter is as good as, so let's not go too much into it. So statistics we can pick up. Coefficients, by default, we have this 5% significance or 90% confidence. So, but it's not a bad idea to have 10% significance or 90% confidence. And then we have some descriptives, collinearity tests. Okay, why don't I click? Here we go. And then Durbin Watson test we take. Then we continue. Is anything in the plots? We'll come back to it. Plots, because when we, at the moment, we don't need to plot anything. Save, yes. Here, we can do 2 things. We can pick up the unstandardized predicted value, which means that at the moment, who is our dependent variable? Our dependent variable is debt to equity ratio. This debt to equity ratio, you all know that it's the actual data. But can you be interested in knowing what would be the theoretical value of the whole column of debt to equity ratio? Then we can click the unstandardized predicted value. And then here also we can find the unstandardized the residual value. Basically, the residual value is the difference between the actual values and the predicted value. I could even click one of them, because this unstandardized residual value will be the difference between the actual values of D to E ratio, which you have, and you will also have the unstandardized, sorry, the theoretical value or the predicted value. And the difference between them is called the residual, but I'm taking both, okay? If you don't know the exact theoretical meaning of these words, these terms, not a big deal. I can explain it to you. Just a sec. The problem is that I got too many pop-up windows here because of this Zoom thing. No. And looks now. Just in case you don't know this idea of error term, let me explain you with this. Let me explain you with a whiteboard that this is our y, this is our x. Our values are plotted all over, and then we plot the theoretical relationship with them. The straight line in the linear regression is a theoretical model, and this model is equal to y is equal to alpha plus beta x. But actually, this model straight line is measuring y is equal to alpha plus beta x. But in reality, our model is y is equal to alpha plus beta x plus the error term. Error term. Why error term? Because what on earth makes us believe that x is the only predicting variable of y? There can be many other variables which we haven't considered. Or x can be many variables, like in this case, we have taken 8 x variables, right? But that doesn't mean that there are not more x variables. There can be many more. And those many more, which we don't know, we combine them in one word or in one term called error term, which means that what we have missed out is captured by the error term. And similarly, what on this planet makes us believe that the form of the variable that we have taken is true? Why do we believe? This is a priori, this is an assumption that the variables are already, the phenomenon is existing because the variables are in the linear form. Not true. And if it is not true, there is an error. And the error term is also capitulating all those errors. That, as I said, the error term is capturing all the errors. Similarly, are the dependent variables even the true dependent variables? Or just because we read some 5, 6, 7 articles and we started believing that, hey, these are the factors affecting y. So there can be many conceptual and practical mistakes that we might have committed knowingly or unknowingly. And those all errors, all those disturbances are captured by this term error. The question is, where is error in this graph? Here is the error. Look at this dot. This dot is not falling on the straight line. The straight line is our theoretical model. And this error term, this is the error term. This is the error term. This is the error term. So all these terms which are deviating, which are not falling on the straight line is our assumed linear theoretical model. Those who don't fit into it, they are called as the error term. And this exactly is the error term which we found in SPSS. Okay, so if you kindly allow me to, so as you can see that this value for example, is a actual value of y for the given x. So if x is x1, then this is the actual value of y. But this one, if I exactly come down and touch the straight line, then this y will be called the theoretical value of y. So I can call it y cap. So I should rather call it y cap. So you can see here that for the same x, or let's say if we have one more value here, let's call it y2. This y2 is against x2. But then it also touches this value on the theoretical line. Then we can call it y2 cap. So for every value of the independent variable, we have the two values of the dependent variable. One is the real value and other is the modeled value, theoretical value, or the notional value. And error term is exactly the difference between the two. So if I want to say error one would be equal to y1 minus y1 cap. Error 2 would be equal to error y2 minus y2 cap. So on and so forth. When at the end of our model, at the end of our column, we will be writing that error n term is equal to yn term and minus yn cap. So this is how. So in other words, this is the beauty of the econometrics, that it doesn't, even though it looks very number based, but it also incorporates the reality, the behavioral side. I mean, what make us believe that this variable is the only variable, x variable is the only variable affecting y, and is it even a variable? Or is it even measuring the right values? So all these things, we basically, our error term is a disclaimer for all our errors and mistakes. Yeah. So this way, so we are done with the statistics, plots, save. Now we have the options. No, we don't need, for the time being, we don't need anything. I don't think we need anything here now. So if we click OK, and now there is the analysis part is going on, and you can see that the model summary is here. See here that the model summary, first of all, it shows the R square. R square shows the explanatory power of the model, and you can see that all our dependent variables, sorry, all our independent variables, X variables, they combine together. They put together are explaining 11% of the movement of the changes taking place in the dependent variable called debt to equity ratio. So 11% is the total. It means that there's still something 89% which is beyond our comprehension, okay? But I tell you one thing, on the practical side, don't take any stress that if your R square is low. R square doesn't have to be 99%, it doesn't have to be. Even if it would have been lower, maybe 3, 4, 5%, I would have been still very happy. So that's not a problem at all. So don't take any stress that our R square is very small. Absolutely not. Adjusted R square is a little bit more rigorous measure, but I think R square is okay, no problem. So, and then Durbin Watson test. Durbin Watson test is basically checking that if there is any autocorrelation between the error terms. As you know that we have seen that there can be the error terms. The question is that, are these error terms too much correlated? The correlation of the error term, the correlation of E1 with E2, E2 with E3, is it too high? If it happens, then our predicted variables value would be going down unnecessarily, or too high or too low. It means that our predicted value could be very much affected, unfavorably. So the Durbin-Watson test is measuring the correlation between the error terms with each other. The question is that what is the safe limit? We have a fantastic Durbin-Watson result, 2.093. As a rule of thumb, if 2 is the safe limit, 2, but if it is 0.25 less, which means 1.75, or if it is 0.25 up, which means 2.25. So anything between 1.75 and 2.25 is fantastic, and which is, in our case, is 2.093. It means that our error term is not very disruptive. Then we move on to ANOVA test, which is analysis of variance. And you can see here that our F value is 3.474, but that's not a problem. We look at SIG. SIG is 0%. When the level of significance is 0%, our confidence level is 100%. We can say with 100% confidence that this R square is significant. Look, I'm correlating these two things. I can say with 100% confidence that the explanatory power of the model is significant. It means it makes sense. It means it's really relevant. Not only we have the 11% explanatory power of the model, but the model is also significant. When I say significant, it means it's not random thing which just suddenly caused this R square up. No, there is a real correlation. There's a real context that why these variables are having an impact, why all these combined 7-8 variables are affecting our dependent variables. So there is a reasoning behind it. It's not just suddenly by chance it happened. And this is measured by the F test. Not only the value of the F test, but more importantly, the significance level of F test. And as we go down, we can see the coefficients. Here, you don't have to worry about anything else, except that you should be looking at the B value and the unstandardized beta, you can call it, and the significance value. I will not even give much care to T value, because if significance is fine, then T value is also reflecting accordingly. Anyways, you can see here that the total revenue is negatively related to our debt to equity ratio. It means that the companies who have more revenue borrow less, basically. And this we can say with 2% level of significance. In other words, we are 98% confident that the total revenue, more you earn the revenue, smaller would be the debt to equity ratio. And then the next variable we have is operating profits return, which is 0%. So we can say with 100% confidence that the companies whose operating efficiency is more, they borrow less. So their debt to equity ratio is less. Return on capital employed, more is the return on capital employed, more is the profitability, more is the debt to equity ratio, which means for the given equity, the companies borrow more if there is a more profitability. And this we can say with 96% of confidence. And the annualized stock return. Annualized stock return, linear form, we can say that the companies whose stock market performance is really going up, the companies which grow more in the stock market, they borrow more. The debt to equity ratio is high. And this we can say with 92% confidence. As I said before, and you could see that when I was addressing the dialog box, by default, the level of significance is 5%, but it will not be a crime against humanity if you take it 10%. So by that logic, we can say with 92% of confidence that the companies which do fantastic job in the stock market borrow more. Maybe the reasoning could be that if you are doing fantastic job Stock market is a indicative of the future growth of the company. It means your growth, your future is bright, and thus you need more resources, more financing, and perhaps your equity is not enough to finance your future growth requirements. Thus, you borrow more. So what I'm trying to do here is that when you have the results, you also need to build up some rational, some argument to support the result. But I'm not explaining each and every variable because I only want to focus on this analysis part, not the interpretation part too much. Look, here I have the squared value of the stock return. And here the level of significance is 24%, absolutely rejected. So you can see that the stock return, but it means that the non-linear transformation of the stock return is not significant. Linear form of the stock return is more, you can see, effective. And you can see that we cubed it, we did all types of things, but the level of significance is very high. So it means the level of confidence is very down. And then we also checked with the index. Is it so that when the whole market is up, not just the company's own stock return, if the index is up, if the market is up, what happens to the company's leverage ratio? And we see here that when the companies, now this is very contradictory to the firm stock return. When the firm stock return goes up, the companies borrow more. But when the market is going up overall, then there's a negative sign. In other words, then when the market is growing, then the companies are choosing to have the low leverage. And I'm only focusing on the significance level below 10. And this we can say with 93% of confidence and so on and so forth. And there is no, so out of corporate governance variables, education is the only significant variable. You can see here about 4%. So we can say with 96% of confidence that as the board of directors, the average education of the board of directors goes up, the company's leverage ratio increases. And this is how we go about it. Collinearity is not a problem at all. So residual statistics, So if you have any questions about the interpretation and the beta values and the significance values, the t values, I don't care much about the t values because if the finding is significant, then the t value will also go up. If you see here, you can see one pattern between t and sig column, that as your significance level is up, the t value is small, but as the significance level goes down, which means the confidence level goes up, the t value also goes up. You can see here, look, 100% confidence, t value is more. 54% significance or 46% confidence, the t value is very small. So those results which are significant, which are really, you want to take them, you would experience higher t values by default. So therefore, as I said before, if I have to focus only on the two columns in the analysis part, I would only look at the first column, unstandardized beta, and the significance column, and that's it. Nothing much, nothing less. So if you have any concerns, issues, so let me share my screen once again with you of the data. And the data is here. And you can see here that there are two more variables automatically added here. And who are they? This is the predicted value of your dependent variable. This, for example, you can. It's very interesting that this is the actual value of debt to equity ratio. This is the predicted value of debt to equity ratio. And very clearly, you can see that the difference is this minus this. So you have the actual Y. This is the Y cap, the dependent value, and this is the residual value or the error term. And where it comes from? It comes from 0.9100 minus 0.76440. That's the difference between the two. So we have already calculated two more variables. Once you click the unstandardized predicted value and the unstandardized residual, then these variables get automatically in the screen. And you can see that once you see your data view, the variable view, you can see that these variables are appearing here, here, and here. Your last variable, according to which when I took from Excel, was D2E, but now we have two more variables. This is a very important part that you are able to go with things. Okay. Yeah, so let's take about 5-6 minutes break, and then we come back, and then we start doing the principal component analysis, the collinearity, which can be a big problem sometimes. Okay, I explained about the autocorrelation, that in case of autocorrelation, your error term, which you just found, the residual term, it can be correlated with one another. So that reduces the predictability of your modeled value of Y, the Y cap, which I wrote. But the question is, what is multicollinearity? Okay, let me explain it to you. If I share my whiteboard and I go to the next one, yeah, and I go to the next one. This is the dependent variable. This is the intercept term, alpha, beta 1, x1, plus beta 2, x2, plus the error term or the residual term. We may be disappointed that it doesn't go like this, but in the heart of our hearts, we want that beta 1 and beta 2 should be significant, so that we can prove that x1 and x2 individually are having a significant impact on the Y variable. So what we want, that if I go away from the language of regression and I start using the correlation, then we want that the correlation between Y and x1, we want it higher. We want it high or higher, whatever you say it. We want that the correlation between Y and x2 should also be high. But there's one problem. The problem is that in certain cases, the correlation between x1 and x2, which means two independent variables, it goes so high that these x1 and x2 seem to be more self-obsessed with they are obsessed with each other so much that they are not fully able to show their impact on the dependent variable. So imagine a situation that R, Y, x1 is below R, x1, x2. Or R means correlation, x2, Y, x2 is below R, x1, x2. If this is the case, there is a possibility of multicollinearity. Multicollinearity means that the collinearity, the correlation between the independent variable is so high that they get so self-absorbed that they are not able to show the true impact on the independent variable. If I say that the GDP of a country, Y, depends on the public expenditure, the fiscal policy, and the amount of currency, monetary policy. And our theoretical relationship is that if there is there's an increasing public expenditure, the GDP of the country will go up. And if there's a rising money supply, this will support the rising growth of the economy and the GDP will go up. But we experience that the correlation between the public expenditure X1 and the supply of money X2 is so high that nothing is left to measure the impact on the GDP of the country. That is a Y variable. This problem can happen sometimes. How do we know it? That this problem exists, or this problem may exist. For this purpose, we need to look at the correlation matrix, which I haven't done when I was analyzing the data. But there's a very, very simple solution to it. There are many solutions, but the one simple solution is that we break up. This is our main model, alpha, beta 1, x1, plus beta 2, x2. I can ignore the error term for some time, not a big deal. And we discover that the correlation between x1 and x2 is extremely high. In this case, this was meant to be our original model, but we can create two models and we can say that y is equal to alpha plus beta 1x, one model, model 1. And then we say that the next model is y is equal to alpha plus beta 2, x2. And this is our model 2. Since now the two models, then I can call it alpha 1 and alpha 2. Alpha 2 here. So what a very good solution or very simplistic solution is that if we are suspecting that the correlation between the independent variable is too high, then we can break up our model and make multiple models. Here you will be doing one regression, but here you'll be doing regression twice. Nothing much changes basically. Or sometimes we have to change the form of the variables. If we find that, if you want to stick with the main model, original model, x, this one, y, and you find that the x1 and x2 are highly correlated, then change their form. Try with the squared values of x1, x2. Try with the square rooted value of x1, x2. Or try with sometime one squared and the other square rooted, and likewise, all logarithmic values. So try to change the form of the variable, and or try to have the lag value. Lag value means you are having a model in which your y1 is dependent on not the current value of the, so let's call it n, yeah. So not the current value of the public expenditure, but the previous value. So for example, the amount of public spending by the government in 2020 will have an impact on the GDP in 21. You can take one lag. You can even take 2 lags. Similarly, you can also have the lag value of the other variables. So the point I'm trying to do is that never shy away from experimenting with the transformation of the variable. You can do in SPSS, you would see when I do the principal component analysis, but at the same time, you can also make these changes in Excel, and then you can transfer the data straight away to the to the SPSS. I think the very lovely function in SPSS is that if you copy the data, the whole data set in Excel and paste in SPSS, you have a choice with variable's name. So pasting with the variable's name, so you don't have to type anything basically. So that's a really very good facility in SPSS. So this is how you can address the problem of multicollinearity. But let's see that if we have this problem of multicollinearity somewhere. So we call it lag value. So you can see that there's a lag of 1 here, lag of 1 year. And here there's a lag of 2 years. So there's a lag of 2 years. If it is a stock prices, it can be lag of 1 day, or it can be lag of 2 days, or it can be lag of 7 days. Whatever. Usually we address. So lag is not always yearly basis. It can be quarterly basis. It can be daily basis even. All right. We need to go to the data. And we need to find the correlation. In fact, we can do while doing the regression as well. If we do once again regression, we have the linear regression. Nothing changes. Statistics. Descriptive confidence. No. Didn't I put the descriptives? Here I think descriptives. Plot save. Does it say correlation somewhere? Even if it doesn't say, no, not a big deal. We can do this way. We can once again go to the, sorry, yeah, here we go. Sorry, I think. Yeah, I hope you can see the data set still. So we can do one thing. We can go to analyze. And here we have a special, so we don't need to go through the descriptive. We can find straight away to correlate. And in correlate, we go to bivariate. Why bivariate? Because we are finding the correlation between two variables at a time. So if I click bivariate, and then I can put all the variables, basically, all the way down. I don't need to have the unstandardized, so yeah, this much. And here by default, we have the Carl Pearson's coefficient of correlation. We do nothing else, and we straight away click OK. And as you can see here, I can check that I'm sharing my screen with you. If I'm not sharing, I share it now. And here we go. You can see that some variables are highly correlated with one another. So you can see that the firm stock return and the log of revenue is highly correlated, highly positively correlated. And here the stock return squared value, which anyway, we're not taking in the regression, so that's not a big problem. So squared and the cubed values are also quite exponential, are quite highly correlated. But the value which we took, which was a significant variable, annualized firm stock return, is quite highly correlated to the log value of total revenue. And when we go up, with the market cap is also correlated, and then we see that, yeah. So what we see that the revenue part, the annualized, what is kind of not so good sign is that the natural log of revenue is not so well correlated with the dependent variable. You can see here the D to E ratio is a dependent variable, and the correlation between D to E and natural log of total revenue is insignificant. It means the correlation between Y and X1 variable is less. But when we see the correlation between X and the other X variables, we see that there is all our independent variables, and they're highly correlated with the natural log of total revenue. It means that when it comes to the natural log of total revenue as a independent variable, there may be the problem of multicollinearity. It could be possible that I have to make multiple models. In some models, natural log of total revenue exists, but in the others, I don't take it, so that I can have that. What happens to the regression if for some time I ignore this variable? Which variable? The natural log of total revenue. So your correlation matrix can be an important indicator whether there is a high correlation between the independent variables, thus causing the problem of multicollinearity. So it could be possible that when you analyze this table more with more scrutiny, you may end up creating multiple models. So instead of having all the independent variables in the one regression equation, you might have to choose. You might consider not taking some of them and instead take them in a different model. So it could be possible that you have to try more than one or more than two, or even several times, the regression coefficient. So this way we can. Sometimes we find that there are variables which could be classified into a factor. So for example, if I take the corporate governance variables, so I find out that we have different independent variables highlighting corporate governance. It could be board independence, it could be education of the directors or expertise. Or if you look at the accounting performance, we have the variable called a return on capital employed, operating return on equity, or earnings per share. If you look at the stock market performance measures, we have the annualized stock return of the company, or we also sometimes use the index annualized return, as we did today for this FTSE 100. Or you can also take some stock market indicators like beta, for example, systematic risk. So you see that you find out that, hey, we have 12 variables. Out of 12 independent variables on D to E ratio, 5 are insignificant, 7 are significant. But when you look at those 7 variables, you find that they can be easily put into 3 broad categories. So rather than considering 7 independent variables which are significant, we see that, in fact, you could have easily placed them into 1 category. Maybe you like this example, but when I had this whiteboard and I wrote that the GDP of the country depends upon the public expenditure and the quantity of money supply. Money supply is a variable, public expenditure is a variable. But what are the factors? The factor is that they both are representing economic policy. And then in the economic policy, you have the monetary and the fiscal policy. So it means that basically they are, even though I take 2 variables, money supply and public expenditure, in principle, I'm studying the impact of economic policy on the GDP. So despite me having 2 independent variables, I have 1 factor called economic policy. The same thing we can do here, that we might find that the return on capital employed is significant. We might find that the operating return on equity is significant, but EPS is not significant. So we can say that we have 2 accounting variables which are significant. Then why don't we call them as 1 factor called accounting performance measure? So instead of calling them 2 variables, we can also say that the accounting performance measures are significant. And then we have corporate governance variables. Those students who are doing research based on the corporate governance as a major variable or major theme, you can see, you can find the corporate governance variables in many ways. You can find that the board independence is one measure of corporate governance. The median number of board meetings attended by the director is a measure of corporate governance. The percentage of performance-based pay to the total pay is a measure of corporate governance. The background of directors, education, experience, expertise, and their other affiliations is a measure of corporate governance. How thick the institutional ownership of stocks is a measure of corporate governance. All these are variables. And then we find, when we regress all these variables as on the dependent variables and using them as separate independent variables, we find that out of these 7, 8 variables which I just named, 3 are insignificant and 5 are significant. Then why don't we call those 5 variables, instead of calling them as individual variables, why don't we call them as a factor called corporate governance? So this way, we can, rather than being more repetitive. So basically, when I say the word repetitive, see the example, the board independence is significant, and the percentage of ownership of the board of director is also significant. Why don't we call both as, instead of calling them 2 separate variables of corporate governance, why don't we say that in this study, in this empirical research, our corporate governance variable is, corporate governance factor is represented by these 2 variables. And we, by combining them, combining these 2 significant variables, we can call it as a corporate governance factor rather than variable. So instead of having too many variables, we can condense them into 1 or 2. This is the whole idea of factor analysis. But please tell me that, do you understand the theory?
Chap, sorry.
And remember, we're doing factor analysis and we go to dimension reduction here. So please remember it. And then we go to the factors. And in the factors, we select the variables which we want to move, who we want to. Look, these are the different variables. So here we will classify them as factors. So first of all, we need to put them all in the activity area. But I will not take the dependent variable. So I keep D to E ratio away. Okay. So once we get this, we move to the activity box, and then we click descriptives. And in the descriptives, you know, the descriptive statistics, the mean, median, these kind of things. In the descriptive statistics, we click univariate descriptives, and we unclick the initial solution. We don't need any initial solution. And then we can put KMO and the Bartlett test. Don't ask me what they are, but you will learn what they are. Continue. In the next stage, in the extraction stage, we click the principal components. So we go with the PCA, the principal components analysis, and we unclick the unrotated factor solution. Rather, we click the scree plots, and we also choose the fixed factor numbers. So let's say that by looking at the nature of the variables, we find out that we have some accounting performance measures, yeah, And then we have some stock market performance measures. And then we have the corporate governance performance measures. Yeah. So if, for example, and where they come from, they look, you choose that in how many categories your variables could be split. When I may be missing something, but when I have a bird eye view of the nature of the variables, the independent variables, it seems to be that they all are clustering on the one side on the accounting measures, then the stock market measures, and then we have the corporate governance measures. So here, if I have to take the factors, I take 3 factors. And when we have this thing, when we choose, we continue. And then the next thing is rotation. And here, if you see, we pick up Varimax, and a rotated solution is fine, and we continue. And then in the almost in the last stage, when we have the options, in the options, we may choose very small values. So basically we see that if the factor's value is too small, we don't take it. And here we can make, as you can see the name here, suppress the small coefficient. So we take anything less than 0.3, we don't take. This is in the theory that if the value of the factor is less than 0.3, we don't take it. Okay, so because other than the factor is not so significant. And then we continue, and here we find okay. And you can see that we have got our factors. But I take you to the main important areas where we need to have discussion. Yeah. And this is this one. You can see that we have 3 factors, or they could call it components. And here we find that all the factor 1 is inclusive of all the stock market based performance measures. So you can see here that the firm stock return is here, the annualized square root, things like that, the annualized firm stock return, and the annualized firm stock return cube. So here we find that there are 4 variables which are basically combining it. But as you know that basically the cube and squared are based on the annual firm stock return. So maybe that could be a limitation, but you can see here that the highest value is, first of all of them are more than 0.3, absolute size 0.3. I hope you can see it, absolute size 0.3. Basically, and one thing more, whenever you see that a variable is in 2 cells, like here you can see that the natural log of total revenue is in component 1 and also in component 2, never take it. Never consider it as a factor. Only take those factors which are only taking, who are more loyal. So they're only, clubbing in only one and only one column, in only one component. If you find that there's a variable which is spreading in more than one component, ignore it altogether. So basically what we find out that the annualized firm stock return cube and the annualized firm stock return and the squared and these, the logarithm, they are basically forming one factor. I give a disclaimer here that because I picked up only one variable and then squared and cube it, but if they were different variables, different names, then I would, so what I want you to imagine that, just imagine that these are not stock return based variables. These are not firm stock return based variable, but these are different names, different variables. It means that I can form one factor, which is an average of this, and this variable. Don't care about the sign. Don't care about the sign. It means that I can form, instead of taking 4 variables, instead of having these annualized firm stock return cube, annualized firm stock return, annualized firm stock return square root, squared, logarithm, whatever it is. But first of all, remember that I assume that these are not based on only on the stock return, something else also. Then I can simply calculate a factor, which is the average of these 4 variables. Component 2 or the factor 2. Natural log of market cap and the market cap. Now this is same, so I will not take both. I will take only one. And then the annualized FTSE 100 return. I can say that the natural log of market capitalization and the annualized firm stock return, they are making one factor, one component. So instead of having 2 variables, I can find the average of natural log of market cap and the annualized firm stock, annualized FTSE 100 return. Ignore market cap. I don't know where it came from. There's no point of taking the absolute value since I'm taking the logarithmic value. So please consider that there's no market cap here. So we take natural log of market cap. So factor 2 is the average of natural log of market cap. And if there were 3 different variables, so it was not market cap, but something else, let's say it was systematic risk, then I would find the average of this, and and calculate a new factor called, I can call it, usually we call factor as, in theory, we use the symbol Z. So for example, factor 1, Z1, factor 2, Z2, Z2. I will not take this value, as I said before, because it's overlapping in a different factor also. So I can't take one variable which is representing 2 different factors. So natural log of total revenue is totally out of my analysis now. And then we see the third factor, which is the median board size, education, experience, and in fact, some of the accounting measures are also mixing up in corporate governance, which is okay, no problem. So we find that there are 5 factors. There are 5 factors, there are 5 variables which are combining into factor number 3. And as you can see here, that the return on capital employed is all zeros. Guess why? It must be that the return on capital employed value is less than 0.3. And I gave a request or a command in SPSS that any value which is below 0.3, I don't take it. So the return on capital employed is not to be analyzed. So this way, we can form 3 different factors or different components. And Stefan, if you take a screenshot, then you can help me in calculating the factors, how we calculate the factors. And please bear in mind that for the sake of this workshop, you assume that this factor 1, annualized firm stock return cube, annualized firm stock return squared, and logarithm, these are different variables. These are not same variables. And here, please assume that the market cap, the natural log of market cap, they're not same, after log value is based on the, the original value. So assume that these are the second part. In component 2, this market cap is not market cap, but something else. Okay, so please assume it. In factor 3, you don't have to assume anything. They all are different variables, so it's perfectly clean. Now we go back to our original data. If I stop sharing it, yeah, and then we go to and we calculate, we transform. Can you see the screen, Stefan?
Yeah.
Okay. So we transform. Here we compute the variable, and let's call it Z1, the target variable. Target variable means what name it should have. And what was the first variable?
Annualized firm stock.
So I put the bracket annualized. Basically, I know that the word annualized is so obvious that it comes 1, 2, 3, 4. So I can take all of them here. Annualized firm stock return. The first value is annualized firm stock return.
Yep.
Sorry, let me do it again. Annualized firm stock return. And then I plus. The next one is annualized firm stock return squared, and then plus. Then the logarithmic annualized stock return. And as I said before, I gave you a disclaimer that please assume that these are different variables. And the annualized cube, and then divide by 4, because these are 4. So if I divide by 4 and click OK, and I quickly show you my data view, and you will see soon that we have a variable called zeta1, Z1. Can you see here?
Yeah.
So there is Z1. So it means that by finding the average of 4 variables, we created one factor, Z1. Same way, we can have Z2. So if you compute variable, and we can call it Z2, and then once again, we can calculate. Bracket is a good idea because then you have less chance of making mistake. The first one is natural log of market cap. Natural log of market cap. And as I gave a disclaimer that please assume that the market cap is a different variable. So I'm just taking it, but technically it's wrong. But I just assume that the market cap is a separate variable, yeah? And we plus, and we add a third one, which is the natural log, which is the annualized FTSE 100 return, which is annualized FTSE 100 return. And then we divide by 3, because this time we have 3 variables. You can put these signs from your computer, or you can use this built-in sign, so no problem at all. And then we click OK. And if I show you once again the variable view, sorry, stop sharing. And if I share my screen once again, and you will see that there is a Z2 variable now. Yep. And then we go to the new, we go to the transform once again, and we have another variable. Let's call it Z3. And the Z3 is, this is much better, much cleaner. And this time we have the median board size. Median board size plus we have the education and experience. We have education. You can only do one by one. Education plus experience. And who else? Then we have the operating profit returns. Operating profits. Yeah. Oh, sorry. I didn't put the plus sign. Then we have the operating profit return. And then I guess we have one more variable, which is price to earning ratio. Price to earning ratio, which means that how much price you want to pay to the stock to earn certain X amount of revenue or dividend maybe. And since we have the 5 variables, so we divide by 5. We divide by 5, and now we can see that there are, if I once again stop sharing my screen. You can see that we have now 3 factors, right? There might be some limitation in the calculation process, but this is the procedural part. So we can see that we have 3 variables. So all different variables are clubbed. Some are deleted, some don't qualify because they're too small or they're overlapping. And then some are good, some are bad, so we combine them. So despite all the hiccups, we are able to make 3 new factors. So let's do the analysis. And now the beauty is that we come back to the normal regression. So we regress linear. Here, our D to E is still R. I hope you can see in the screen, yeah?
Yeah.
The D to E, which is still R. Dependent variable, what we do that we send all these independents home. And instead, now we don't take the variables. Now we take the factors. So what we do, we only take factor 1, factor 2, and factor 3 and put in the independent in the dugout. And here we find the statistics. Well, yeah, that's fine. Descriptive, Durbin, Watson. We don't need actually anything now. This is all good. And we click OK. And here we find that our R square, sorry, I share my screen. My R square is very less, but that's not a problem. Durbin Watson is fine. But the problem is that our R square is very insignificant. You can see that there is a 20% level of significance. Maybe it's possible that I took some, all my first variables are based on the stock return, and then I took market cap 2 times, one the actual and the logarithmic value. Maybe that is a limitation, but my point is not that how beautiful my results are. At the moment, I'm only focusing on a new technique that you can use the ANOVA, and then we find out that except for our first factor, all other factors are insignificant. So only Z1 is the significant variable, which have an impact. So again, I'm giving a disclaimer that don't go to that, are these results better than the regression results, which can be, or worse? Of course they can be. If your principal component analysis is not doing so well, then it also gives you a food for thought that maybe we should stick to our old classical multivariate regression analysis. It means that these variables are not really truly forming the factors. So it's better to go back. But I would still like to test that if we don't take market cap twice, if we take only the log value, and if we only take one value of the stock return, does the result improve? I have a doubt, I have a hunch that the results would look much cleaner in that case. But then we also took one factor called Z3, which was fine, okay, but that is coming to be insignificant here. So here, when I see these results, I may tend to believe that I think our principal component analysis is not doing so well. So we go back to our old classic multiple linear regression. So, but the whole idea is that sometime you may be considering that instead of having too many independent variables, why don't we condense them into factors and then see how it goes. So this was all about the PCA analysis, the principal component analysis, where we convert the variables to factors. And there's no assurance, there's no guarantee that the next stage analysis would give you better results than the previous stage. So there is no assurance. As we have seen with our own eyes, despite there are some issues with the way we define the variables, okay? So, but I would still be intrigued. The last thing I would like to do that I would try to recalculate my, these variables. So, for instance, residual 1, zeta 1. Yeah. So maybe I quickly transform these variables once again very quickly. Stefan, can you show me what was the Z1? It was based on the return. Yeah. So if we calculate Z1 again, I can replace it. And it was only based on the stock return, right? Yeah. So if I only take the annualized firm stock return, yeah, this can be Z1, change existing, yes. And what was the Z2?
Was the natural log.
Natural log. So if I calculate again my Z2, and this time I only take the natural log of market cap, and not the, sorry, I'm just trying to take away this first and then share my screen. And what was the third variable?
Annualized FTSE.
Annualized FTSE. So if I have only natural log of market cap, yeah, and then the annualized FTSE. Annualized FTSE comes here, and then divide by 2. And we have now third variable was fine. So if I go once again to the data and we go to the stop sharing. So if I go to the data view once again, now we have recalculated our variables. So analyze, regression, linear regression, because I've changed the form of these variables. So I send the old ones back and bring them back again. So we have now Z1, Z2, Z3. Z1, Z2, Z3 here. And then click OK. And we find that our R square has slightly improved, 2.5%. And guess what? A Durbin Watson, huh?
You have to share this.
Oh, my apologies. It seems that things are slightly better than before. Our R square is 2% and the Durbin Watson, but this time our F test is significant. Look, our F test is significant, which means that now we can say 99.5% confidence that the explanatory power of the model is good. And see what, I'm not surprised. Remember when we were using multiple regression model, our R square was 11%. Why so? Because more X1, X2, X, more independent variables you have. We were having about 12 independent variables. More independent variables means by default, your R square would be higher. But this time we have only 3 independent variables called Z1, Z2, Z3. So definitely your R square would be low. That is why I'm saying that R square high or low doesn't matter. What it matters is that, is it significant? Yes, it is significant. Look at this, 99% confidence that these factors are making an impact. And then we look at the coefficients and we find that now our Z1, which was absolutely junk in the previous analysis, now this is significant because we calculated stock return too many times. That's why. So this is the beauty of the principal component analysis, that it can filter out the unnecessary things. And then now we see that our Z3, which was significant because of some error, now it has been corrected. Our model's explanatory power has improved. Our F-test significance has improved. And now we can see that the Z1 factor is significant. Okay, so this is the principal component analysis. And once again, I repeat, there's no guarantee that a higher level analysis brings you the better results. Well, it should, but it's not always true. So when I compare my multiple variable regression model and the principal component analysis, I don't see a big change. I don't see a big improvement by using PCA factor analysis in this case. So I may stick to based on these two comparisons, I may choose to stick to, in fact, my multiple correlation, my multivariate regression, multivariate linear regression analysis. Okay, so I don't see much difference. Yeah. So this is all about these two techniques that we discussed today. Tomorrow we will have some linearity tests, some stationary test. We will be also doing the general linear model, regression model as well. And if the time allows, we can also try with the two-stage linear least square method. So thank you very much for today and hope to see you tomorrow.